So this is 12, 16, 14. Okay, N2. What's our first step if we're doing Gooch method? Count something. Count the valence electrons. So, nitrogen has how many valence electrons? 5. And you got that information from where? Periodic table, because group 15, therefore, yeah. Group 15, so it's got 5 valence electrons. Okay. How many nitrogens do we have? 2. So we have 10 valence electrons. Okay. All good so far. What's our second step? Yeah, we count up the octet. So nitrogen is not one of our weirdos. Nitrogen would like to have 8 electrons. There are 2 nitrogens. If everybody had all the electrons that they wanted independently, there would be 16 octet electrons. Okay, so far so good. Step 3, what's that? Yeah, subtract valence from octet. So there's 16 that are desired, 10 that we actually have. So how many do we have to share? 6. So there will be 6 shared electrons. Okay, I'll shrink this. Now, step 4. How many bonds are we talking about here? 3. Because a bond is 2 electrons, so divide by 2, that gives us 3 bonds. There's only one step left. What is it? What was that, Kira?
Subtract bonds from valence. Oh no, the
shared electrons from valence. So we know that we started off with 10 valence electrons. We're sharing 6 of those. What we'd like to know is how many we're not sharing. We have 4 unshared electrons, which means how many unshared pairs? Sometimes called unshared pairs, sometimes called lone pairs. We have 2 lone pairs. Getting back to where we were. Well, you've got 2 nitrogens to hook up. How many places are there to stick 3 bonds? Where can you stick a bond here? I only see one possible location. Triple bond! It's very exciting. I encourage you to do that when you make a triple bond. I should clean my triple bonds up. I got too excited. Okay, we've got our bonds in there. And nitrogen does this a lot. Nitrogen triple bonds very often. It triple bonds to itself, it triple bonds to carbon, it triple bonds to anything that'll hold still long enough to let it form a triple bond. So, where do those lone pairs go? Where do you see possible candidates for lone pairs? You can take a guess on your own paper. And does it matter if you have them, on the top or on the side? No, it doesn't. Oops, it does matter if you have 3. It doesn't matter where you put them. Traditionally, we show it this way because we have that whole thing where these electrons want to be as far away from one another as possible. This is, best friend. Blah. So they're pushed out to the sides is typically how it's shown. Seem easy enough? Okay, good. Okay, I'm going to take this slide out of order because I want to talk about polyatomic ions. There comes a point in every kid's life where somebody has to sit them down and say, it's time to talk about polyatomic ions. Today's the day. I know. You've all been excited about this for probably your whole lives. So this is out of order because your book handles it in a different sequence, but I think it works better to handle it here. A polyatomic ion, well, it's an ion. Poly meaning more than one. Atomic, made of atoms. A polyatomic ion is an ion made of more than one atom. So what we have is we've got a group of things that are sharing electrons that then either pick up electrons from out in the environment, out in the wild, or give up electrons. So we're going to start off with a really easy example, and the one that you will use a whole lot. Whoops, that's not the right color. So we've got hydroxide, OH1. Very common. Sodium hydroxide you're going to use on Thursday in your ornament lab is a sodium plus a hydroxide ion. We use potassium hydroxide. We have lots of interesting hydroxide compounds. We hook this onto methane, and we can make racing fuel. Great little ion. Handy little thing. So let's step back to just drawing a Lewis structure of a hydrogen and an oxygen. If we step back to drawing an electron dot diagram of these two things, it would most traditionally be drawn basically like this, right? Do you see any intuitive way that you could hook those two things together? Yeah, I think you all do. That look good? Got any problems with that? What's your problem, Ms. Long? Oh, we have this singleton electron hanging out there. No partner. And we said we can never, ever, 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 ever have a single electron. We can have lone pairs, we can have unshared pairs, but we can't have one electron. Are there electrons running around in the wild? Yeah. You've probably picked some up if you've walked across carpeting with, wool socks and then touched a doorknob. You've gotten rid of them. Woo! So yeah, there are electrons all over the place that can get pulled off of things and put onto things. Well, if this whole little covalently bound system picks up an electron, what's its charge? Do you have one more electron than you started off with? 1 minus. That is the Lewis dot. And of course, if we were drawing this and we were being, really finishing this up, we would have to change that to a dash. Do that. We have a hydroxide ion. And for ions, and I think I may have misspoken yesterday, ions are what get the brackets, and I'm not sure if I said something different than that yesterday, but I want to correct myself if I did, and I'm on the record correcting myself. Ions get a bracket. They always have to have a bracket and show their charge, period. Have to do it. That's just the way we do it. That's the way we do it, period. So let's try one that's a little bit more challenging. Now, what if we were going to, can we do the Gooch method on these? You might suspect that I wouldn't ask if the answer was no. Yeah, we can do the Gooch method on these. So let's go with sulfate. We'll go to the next slide. Sulfate is SO4 2 minus. And the first step looks remarkably similar with one twist. What's the first step when we're gooching any Lewis structure? Count valence. So we've got sulfur with 6. We have 1 sulfur. We have oxygen with 6. And we have 4 oxygen. So 6 and 24. Now, there's a difference here. If we have a charge, we have to account for those extra electrons. If we have a 2 minus charge, have we lost 2 electrons or gained 2 electrons? Gained 2. So we have plus 2 extra, which gets us 32 valence electrons. So this is the critical piece if you're gooching a polyatomic ion. I just like saying gooching as a verb. It's fun. Okay, step 2, no change. So step 2 is count your octets. Sulfur wants 8. Oxygen wants 8. Times 1 times 4. 8 and 24. 8 and 24. 32. Yes, it is. I knew there was a problem there somewhere. Woohoo! End of the day. Can't think anymore. Okay. So we have 40 octet electrons. So what that means is if every single atom in this little cluster had everything it wanted for Christmas, there would be 40 electrons in this whole bundle. Well, we got to share. So step 3, same as it was. We take our 40 octet electrons and we subtract out the number that we actually have. So 8 electrons are going to be shared. We will have 8 electrons that get shared. And now we just want to know how many bonds that is. Well, that's pretty easy. 8 divided by 2, we're going to have 4 bonds in this thing. Here comes the shocking number. Are you ready for the shocker? This is the absolutely astounding number. So we figured out how many unshared electrons we have, right? How many unshared pairs we have. We have 32 valence electrons, and we are sharing 8 of them. How many unshared electrons do we have? A whopping 24. So 24 unshared electrons divided by 2, that gives us 12 lone pairs. Okay, I'm going to shrink all of this so that we can keep our numbers at least in some semblance on the same page as our drawing. Whoops, that's not what I meant to do. That didn't work out either. There we go. Okay, so we're looking for 4 bonds. We've got a sulfur and 4 oxygens. What's going in the middle? Sulfur. You know, and it's partly down to that whole, we got 1 of you and 4 of you. You go in the middle. So, you know, just to start off, sort of noodling around, hey, that would be 4 bonds, right? Okay. Well, where do we put those 12 pairs? 1, 2, 3. Oh, there's 3 pairs. 1, 2, 3. There's 3 more. 1, 2, 3. Oh. Oh. Looky there. Are we done? What's wrong, Claire?
Needs brackets.
Needs brackets and a charge. Now we're done. Not so difficult. Now, do you remember resonance structures from yesterday? We're going to do one more together before I cut you loose. And this is one that combines the resonance structures from yesterday with the ions from today. Oh boy, oh boy, oh boy, oh boy. One of my favorites, NO3, 1 minus. It's called the nitrate ion. Ammonium nitrate fertilizer, the bomb that blew up the Oklahoma City Federal Building. Ammonia nitrate, compound made with this stuff. You find nitrate in saltpeter. You find it in gunpowder. You find it in smoked meats. It's added to hams and bacons and other kinds of cured pork products. And it retards spoilage. So it does lots of good things. First step. Everybody else coming up with the same thing? Their first step? And what we did in the other class that I thought worked pretty well was if you want to try this on your own, get as far as you can. When you get to the point where you have questions, stick your little head up and I'll kind of do each step and check in, and you can check in or not. Yes, that is 24. Okay, so I've come up with 32 octet, 8 shared. Everybody else? Wunderbar. Sixteen unshared, 8 lone pairs. Okay, now comes the fun. Who started doing their structure? Okay, this is the juicy part. Stick those down there. Well, what's going to go in the middle? Nitrogen. We got 3 oxygen to stick around it. Okay. Start sticking in bonds. 1, 2, 3. We have a problem, Houston. 1 more bond is needed. What does this mean? Double bond. Okay. So checking our octets, is nitrogen happy at this point? Yeah, nitrogen's satisfied. We're done with nitrogen. Where do all of those unshared pairs go? Well, they seem to be headed destined for the oxygen. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wait, 2, 4, 6, 8, 10, 12, 14, 16. Okay, I can't count, but we knew that. Are we done? What do we need, Ella?
Brackets and charge.
Okay, brackets and the charge. Are we done now? What do we need? What do we need, Kaylee? Oh, crud. Yep, we got resonance here. So I'm going to copy this to the next slide. I'm going to shrink it a little bit. Because there are 3 locations that that double bond can appear in, we have to show it in every single possible location. So we're going to do our double-headed arrow. Okay, are we done? 1 more to go. That's sounding a bit more interesting. Okay. That is our finished structure for a nitrate ion. If you don't draw all the resonance, it's wrong. If you don't draw the brackets, it's wrong. Questions that occur to you before I tell you what people had in the other class?
We have to draw the structure if there's a double bond.
If it can be in more than one location.
Okay.
Yeah. This is only needed if there's something that can be in more than one location. So, in something like, what was it, CO2 we did yesterday? Do we have to draw resonance for that? No, because it's always going to be double bonds on both sides. Now, if only one of those was a double bond, we would have to draw resonance because it could be on either side. Okay, other questions? I can tell you the one somebody came up with, and if you look at this one, it's clearest. So we always put the two unshared pairs on the one with a double bond. How do you figure out where the unshared pairs go? Check octet. So if we look at this from a perspective of looking at the octet number, is this oxygen happy? 2, 4, 6, 8. Yeah. Is this oxygen happy? 2, 4, 6, 8. Yep. Is this nitrogen happy? 2, 4, 6, 8. Yep. Is this oxygen happy? 2, 4, 6, 8. Yep. So you always want to look at octet. You don't want to stick a third unshared pair on something that's got a double bond. Then you've gone over octet. You don't want to put only two unshared pairs on something that has a single bond for this example. Make sense? Okay, you've got some time to work. We'll probably work up to about the first bell, and then we'll do some new stuff.